Welcome to Paris System 147. In this podcast, we're discussing whether you can use 3D printing to print and investigate helicopter rotor blades. There are two very good reasons why this is interesting. The first is that when you 3D print something, particularly with the FDM method, as we'll discuss later, the surface is quite rough. So a good question is whether this surface roughness affects the results. The second reason why 3D printing helicopter blades is interesting is because partly with FDM, the blades will be much weaker because of how the material is laid down. There are literally periodic weaknesses in the blades as you go along, and whether these weaknesses even hold up to the forces on them is interesting because you have these blades rotating around. That's a lot of force on them. So looking into using 3D printing to print helicopter blades, we are using a paper called Wind Tunnel Testing and Validation of Helicopter Rotor Blades Using Additive Manufacturing. And additive manufacturing is just where you put material on each other, so you add material, hence additive. So this is open access, and you can find it in a link in the description like usual. So let's begin. So the motivation for this research is purely practical, whereby 3D printing helps us make models much more cheaply and quickly than traditional manufacturing techniques. And in some situations, you can make more complicated models than what you could with traditional manufacturing techniques. But in this particular case, with the helicopter rotor blades, that's not really a limitation of regular manufacturing techniques. Like you can CNC a blade quite easily or use it like metalwork or whatever. So that's not really an issue here. It's more the cost and the time that it takes to make a blade. And 3D printing is usually much cheaper and much quicker in this particular case. So for this particular research, these researchers using CFD and wind tunnel testing mostly for validation purposes. And we'll also see some other interesting results there. So for their models, they made the CAD models first and then sent them to the slicer, which is the software that transforms the CAD model into the code that this 3D printer needs to print, as well as adding the various details for the printing temperature, for example, the speed, the heated bed temperature, the cooling, and so on. So they tested these airfoils at Mach 0.3, 0.4, and 0.5. That is pretty impressive because, again, these are just 3D printed models. And to be spinning around at Mach 0.5 cruising speeds, so it means you have not only the Mach 0.5 speed as you cruise along, but also the spinning speed, the RPM. That means there are a lot of stresses on them. There's a lot of centrifugal force on them. So interestingly, I have had quite a lot of experience with 3D printing models, and particularly for rotating situations. So they were for different spoked patterns for car rims. These parts also spun around at a very high speed. The cars were traveling at 140 kilometers per hour. They were also fine, mostly. There are a few accidents, but that was to be expected, so the proper precautions were taken beforehand, and no one was hurt or anything like that, so that was completely fine. The wind tunnel wasn't damaged. It was just a couple of these things flew off sometimes and broke. But if you design them well, that doesn't happen. So overall, I was very impressed with how well these 3D printed parts held up. One thing to note is that the parts that I was testing were printed with a SLA printer, and that is different to FDM, and we'll go through in a second what the differences are. So I think it's good to talk about these two different methods because they're the main ways that we print models these days. The first one is FDM, the second one is SLA. While they are both 3D printers, there is a very big difference between the quality that comes out. So historically and even today, SLA printers are far higher quality than FDM. The surface roughness is uniform, while for the FDM approach, the surface roughness has this periodic waviness, and it is to be expected because of how the layer of plastic is deposited or whatever material you're printing. So you can print even stone or like wood and even like a carbon fiber kind of thing. But anyway, so the FDM printers work by literally heating up plastic, so a thermoplastic, not a thermosetting plastic, and then they squeeze this plastic out through a nozzle and lay it down in the right place. As you complete one layer, you then move the nozzle up to the next z-axis height and do the same thing, and you repeat this process until you have finally finished the part. FDM also stands for fused deposition method, which literally means you're depositing a finite amount of plastic at a time and fusing it to the other bits that you already deposited. So contrasting that with SLA, SLA stands for stereolithography. The way that this 3D printer works is that you start off with a liquid, and this liquid is effectively liquid plastic. Technically, it isn't a liquid plastic because a chemical reaction is needed to take place in order for it to turn into a plastic and a solid plastic, but it's close enough. So how this works is that you have a vat of liquid, and underneath it you have usually usually underneath it, you have this light source, and this light source gets concentrated to a certain point in the liquid. The point at which this light is concentrated then undergoes a chemical reaction, effectively curing it and turning it into a plastic solid. Then once you finish the part, you need to finish the curing process and rinse it. You then have the final part. In addition to the more uniform surface roughness of the SLA, you can typically get finer details. So for example, if you want to emboss something like a size 10 font writing onto an object, the SLA printer can do that very crisply, whereas the FDM printer will struggle with a clear embossing, especially depending on which direction you go in, but the SLA is really nice. So the SLA also works in layers, but the layers are not nearly as fragilely fused together as with the FDM printer. That means that the FDM printers usually put out weaker objects. And again, it depends on the temperature you extrude at, the cooling temperature, the speed at which you're going at. There are a bunch of different properties that do affect whether this part will be strong or not. So hence why this paper is very interesting to me, because they are using FDM for an application with a lot of forces and in different directions. So you obviously have the forces from the lift, drag, and the moments, but you now also have the centrifugal forces to contend with, which can really take advantage of these weaknesses between each layer. And again, depending on how you print it, you may be able to get away with putting the layers in a direction which aren't susceptible to this centrifugal force as much. But if you do it in the wrong way, then these layers effectively form a shearing point that the object can shear across. So let's get back to the CFD setup, because we've talked about 3D printing now. So for the CFD setup, they use an unstructured mesh, which is good for modeling the finer details, but the downside is the increased number of cells. As we'll see later, they used quite a lot of cells, which means that they did their best to get good accuracy, which is good. They also looked at a bunch of different turbulence models, which I should go up to here. We can see the different turbulence models here. So they have the experimental results in this blue. They have the realizable K-epsilon, SST K-omega, which is generally my favorite for like plug and play kind of situation. You don't have to think too much about the situation. If you want to think more about the situation, then you can fine tune it with different turbulence models. So the SST K-omega is here, the K-omega, and then the RNG K-epsilon approach. So because they're using turbulence models and they don't talk about time steps, we can pretty much conclude that they used RANs here. And in figure 1, we can see how the results on the lift for these blades were affected by these different turbulence models. And this is great because often we just talk about how the turbulence models affect the flow, etc. But now we have, for the exact same application, different results. So you can see that the experimental line is right here. This is the blue line. And I should mention, if you're listening to this on Spotify or Google or whatever, you can watch the video on Spotify and or our YouTube video, on our YouTube channel. And on our YouTube channel, we have other goodies as well that you can look and learn about aerodynamics and some fun simulations as well. So in figure 1 here, we see this blue line, this third one from the bottom. That's the experimental results. And then we have some grouped results. So for example, the K-epsilon and RNG K-epsilon, they kind of group together on this bottom part here, but you can see the major difference between the RNG K-epsilon results and then the K-omega results in this light blue. You can see there's like a 20, 30, 40% difference sometimes in the lift force prediction. So that's how much of a difference these turbulence models can make to your simulation, which is why it's important to get the right turbulence model. So to determine which one was best, they said that the realizable K-epsilon one was best, and they don't say exactly why, but I'm pretty sure it's because they compared it to the experimental data. So they weren't explicit in saying that the realizable K-epsilon model, which is this like ready one here, that was the best because it modeled the experimental data best, but I think that's what they mean. That's why they did it, because it is the closest, with the SST K-omega being very close as well, but there are some minor differences. So just looking at figure 1, we see that the standard K-epsilon and RNG K-epsilon results gave very similar results, and that is because they are very similar in their turbulence modeling. The realizable K-epsilon is a little bit different. Their turbulence models, the equations they use are a little bit different in this case, which were beneficial for this exact situation. So to be honest, I don't see too much of a difference between the K-epsilon or SST K-omega, as I mentioned, except for one situation where it's 19 meters per second, where the SST K-omega jumps up quite a lot compared to the realizable K-epsilon, and the SST K-omega sort of mimics more the K-omega. So the SST part is significantly better than just the standard K-epsilon model, and that is what it's supposed to be doing. So in terms of, so they're going forward with the realizable K-epsilon Terms model here, which is they found is best in this situation. So in the terms of the grid independence test, they looked at 4 different mesh resolutions. So let's go down here to see these mesh resolutions. We have in table 2 them shown here. So the coarsest mesh had 5.8 million cells, while the finest mesh had 10.9 million cells. Then the other 2 coarseness or finest meshes had between these 2 values of 7 million and 10 million. So they use the lift coefficient as the value to measure the grid convergence by. In this figure 4 here, they have the lift coefficient on the y-axis and the number of cells on the x-axis. Their study definitely shows that their mesh was approaching independence, but there was still a small change of 1.5% in the lift coefficient between the finest and second finest meshes, as we can see here, the error between the lift. So they concluded that this was good enough for convergence, and I believe that they used the finest mesh of 10.9 million cells, but they don't say explicitly from what I can read. One thing to note is that they used a y plus value between 30 and 50 for all of the grids. As they are using the realizable K-epsilon terminus model, these values are acceptable. So one thing that is important, so I'm going to discuss what the y plus value is first, then talk about how the terminus models tie into that. So one thing to note is that the y plus value is effectively a way of telling us how well resolved the boundary layer is. What that means is that the closer to 1 the y plus is, the more important parts of the boundary layer are simulated. So the further away from 1 it is, the less accurate it is effectively. But depending on the terminus modeling, we can get away with a coarser y plus. So for particularly the K-epsilon family, we can go to like a y plus of 30, 40, 50, and generally speaking, these terminus models are going to be okay, or at least they're not going to suffer any degradation in performance. Like if you go to a y plus of 5 or 1, which is more ideal, the K-epsilon isn't going to give you too much of a better result than like the K-omega. On the other hand, then if they had like a y plus of 30 or 40, so the K-epsilon is really somewhat independent once you go down past 30 for the y plus. On the other hand, for the K-omega family, you need to have a y plus of like 5 or lower, which means you have to have a much finer mesh, particularly in the boundary layer, to get good results. And if you go from like 1 to 5 to 10 to 50, you're going to see a major difference in the flow physics and then the lift and drag forces. So this is probably one reason why the realizable K-epsilon performed better than everything else, because in this particular case, they had a fairly high y plus of like 30 to 50, and the K-omegas aren't going to be able to contend with that because they need a y plus much lower than that. So that's one reason potentially why the realizable K-epsilon came out better here. So let's move on to their wind tunnel testing, because this is where they put the 3D printed parts into the wind tunnels. So one thing that is quite important to note is that they say in relation to the blades, let me find it here, just here. They say the actual size taken for the analysis in CFD is 12 meters for the blades, but the test section size is 0.6 meters by 0.6 meters. The model was designed for 500 millimeters with 200 millimeter blades and 100 millimeter hubs. So what this means is that for their CFD, the blades were 12 meters long. For their experiments, it was only 200 millimeters long, and that's because the experimental set up their wind tunnel had a much smaller cross-section, obviously, than a 12-meter cross-section. That would be one of the biggest wind tunnels in the world if they had that. So this presents us with a problem. So the key thing when doing CFD and using wind tunnel data to validate your CFD is to use the exact same setup in your CFD and your wind tunnel. If you don't do that, then you're not really comparing the same thing. That also means that you need to have the identical geometry. So if you have your test section of 600 by 600, in your CFD, your domain has to be 600 by 600. Here they don't do that. So there is obviously a large difference between the CFD, where the blades were 12 meters long, at least that is what I can tell here what they said, and the wind tunnel, where the blades were only 200 millimeters long. That introduces a lot of potential differences, and the funny thing is that there may not be anything wrong with their CFD, but because the CFD setup was different to their wind tunnels, you can't expect the data to match up like 100%. So effectively, the CFD is right, the wind tunnel data is right, but because they're under different conditions, they're not going to match up, and that's going to cause a potential problem in the validation process. And one thing to note is that another thing that most aerodynamicists don't do is take into account the density of air when they are doing experiments. The reason why this is important is because when we're doing experiments, we usually only looking for a few percent changes. So we might do like one airfoil and then do another airfoil, or one type of car and another type of car. We might get like a 3% change in the drag or lift. So that's not a lot, and the problem is that the density of air changes by that much throughout the day, and even more between days, weeks, months, and seasons. And the experiments take place over more than one day usually. So when you get your data from your wind tunnel, usually there'll be like an inaccuracy of 5 or 10% from the change in air density, which you don't even know about. Then you go to your CFD and you set up your CFD using a certain density, and the density of air you used just that you specify in your CFD isn't going to be the same as your experiments, because how could it? You don't know what this density was in your experiments. So you can't factor that in when you choose the right velocity, for example. So this is naturally going to result in a mismatch between the CFD and experiments. That makes it hard to get trustworthy results, and you don't even know it. So to solve this problem, we here at Aerodynamics make an instrument called the Atmosphere Hawk. It accurately measures the density of air, and it is very reliable. You can find it in the description, so it gets rid of that error for you. So one really cool thing about their wind tunnel is that it's made of wood, as you can see in figure 5. You can see the contraction leading down to the test section, then to the exit. It is a blow down wind tunnel, so it's not it's an open wind tunnel, it's not a closed return. So one thing about open wind tunnels is that they're much easier to make, and they don't need nearly as much room, so you can make a bigger wind tunnel, like in terms of the cross section, and not have to have it as big a facility. Whereas for a closed return, you need to have a much bigger facility because you have the other 3 sides to the wind tunnel. Also, the closed down is going to be quieter, and you can usually get higher speeds out of the wind tunnel because you have the air going back around already at a velocity. Whereas for the open wind tunnel, so this blow down, for example, you need to accelerate the air from 0 to whatever velocity you need. So you need to give even more energy to that. But it's pretty cool how it's made out of wood. Like, you don't see too many wind tunnels made out of wood these days, and it's just like a cool like throwback relic kind of thing. I don't know if it's new or not, but it just looks cool. It's like retro kind of thing. So anyway, in figure 6, you can see the 3D printed blades. The 3D printing process is much more noticeable for the black blades than the white blades. So the black blades, you can see quite clearly the different layers. There's like different white parts. Let me zoom in actually. Let's see if we can see it a bit better. So you can see how like it comes out in these strange white sections. Those are the different layers. Whereas with the white part, you can't really see that too much. So from what I can tell, they didn't sand the blade smooth, and speaking from experience, that is something you can definitely do with 3D printing, but it takes a lot of time and a lot of care. So you need to be careful around the trailing edges, and if you do the sanding, you can get the surface roughness down to like 5 microns, which is very smooth and comparable to other machining techniques. So let's move on to the results. So these researchers looked at 2 different types of blades, one called the HH02, and then one called the NASA SC2-0714. The difference is that for the HH02, it's what's called a reflex airfoil, and that is where the airfoil trailing edge pops up at the back. The benefits of this type of airfoil is that the moment about the aerodynamic center can be 0. So what that means is that it is inherently stable. On the other hand, the NASA SC2-0714 is a supercritical airfoil, and a supercritical airfoil is one where the critical Mach number is as high as possible. So what this means is that the airfoil can travel closer to the speed of sound without sonic flow occurring over it, hence it doesn't experience such a great wave drag. In other words, it produces less drag near the speed of sound. So the results of the CFD at Mach 0.3, 0.4, and 0.5 are shown in tables 3 and 4 for the HH02 and the NASA SC2-0714 respectively. So it is clear from the lift and drag ratios, so the lift and drag ratio is here and here. It is clear from these ratios that the NASA airfoil is much better. So it hovers around the 13 mark, while the HH02 is around the 7 mark. Interestingly, as the Mach number increases, so from 0.3 to 0.5, both the HH02 and the NASA airfoils experience improved lift to drag ratios. And this was mostly because of the drop in the drag coefficient. So you can see for the HH02, for example, when the Mach number went from 0.3 to 0.5, the drag coefficient dropped from 0.059 to 0.054. And likewise for the NASA airfoil, it dropped considerably as well. So that bump up in the lift drag ratio came about because of the drop in the drag coefficient and a little bit of an increase in the lift coefficient, but not nearly as much as the drop in the drag coefficient. So now for the experiments. From what I can tell, the blades survived the spinning, which I'm a little amazed at because of how great the centrifugal forces would be at Mach 0.5, and the fact that this is a FDM 3D print, which isn't that strong. The layers are not really fused together that well, but they survive, so that's pretty impressive. So Table 5 and Table 6 show the results for the different RPMs of the HH02 and NASA airfoils respectively. The RPMs went from 500 RPM to 1000. And here, as in the CFD, the lift to drag ratios for the NASA airfoil were always about like 30 to 50% better than the HH02 airfoil. So we can see here the aerodynamic efficiency, L/D, it ranged from 17 to 21, whereas for the HH02, it only ranged from 11 to about 15.5. For both airfoils, as the RPM increased from a minimum of 500 to 1000, the lift to drag ratios dramatically increased. So for the HH02, the lift to drag ratio increased by like 50% over this RPM range, while for the NASA airfoil it increased by 25%. It is kind of difficult to tell whether this improvement came from the lift or the drag, but if we look at how the lift and drag were affected across the RPM range, we will see for the HH02 that the lift increased by about 325% when you increase the RPM from 500 to 1000. So that's 425%, not 325%. And the drag only increased by about 275%. So the lift increased by a factor of 4, whereas the drag increased by a factor of 2. So we can tell that because the lift increased by so much compared to the drag, we can conclude that the lift to drag ratio increased mainly because of the the lift, and not so much because of the drag. And a similar conclusion can be drawn for the NASA airfoil, where the lift increased by about 400%, while the drag increased by about 300%. So we can say that the increase in the lift to drag ratio was mainly because the lift improved at a greater rate compared to the drag over this RPM range. So moving on to figures 13 and 14, let me zoom out a little bit here so we can see. So figures 13 and 14, we see how the lift changed for the HH02 and NASA airfoils, respectively, when the RPM and velocities changed. So we have a nice 3D surface plot here for each one. And the, I guess that's x-axis has the RPM, the y-axis has the velocity, and the z-axis has the lift force. So interestingly, the trends are not the same. So for the HH02, which is this top one here, increasing the RPM across this x-axis here, while holding the velocity constant, actually reduced the lift produced. Whilst for the NASA airfoil, the opposite is true. If you increase the RPM, so if you hold the RPM constant while increasing the velocity, the lift increased. So it's the exact opposite trend for these different types of blades. So in figures 15 and 16, let me zoom out a little bit here again so we can see both of them at the same time. So in figures 15 and 16, we have now the drag changes with the RPM and velocity for the HH02 and NASA airfoils respectively. So they both had the same trends here though now. So while the lift had the opposite trends for these two different blades, the drag follows the same trend for both of these blades, which is if you keep the velocity constant and you increase the RPM, or you keep the RPM constant and increase the velocity, the drag increases. So that is the end of this paper. I really liked it. I really appreciated how the 3D printed models held up to the forces, and it was pretty cool seeing the different results here. So with that, my little analysis, we come to the end of this podcast. And if you liked it, make sure to give it a thumbs up. And if you want to see more like this, click the subscribe button or the follow button, whichever platform you're on. And if you want to get better at CFD and or theory, check out our courses in link in the description. You'll get better at like figuring out the CFD. For example, we went through how to do this grid independence study. We went through this terminus modeling. We go through this and a lot more in more detail in our CFD courses below. So you get really good at CFD. And if you want to get better at experiments, for example, we went through before how the density of air changes by 2 to 4% on a regular day. And that is because that's going to result in an error in your experiments. And we make an instrument called the Amsu Hawk. And the reason why this is important is because the density of air is is affected by the temperature, barometric pressure, and humidity. So having even you in the wind tunnel, for example, changes the density of air because you're pumping out heat and more water is going into the air from your breath and sweating and etc. So the density of air will change by even more than 2 to 4% between days, weeks, months, and seasons. 10 to 15% changes are very normal, which means that you need to take into account these changes when you're doing experiments. What's more, if you don't take them into account, then you are not only are most of the things you're finding in your experiments are just random error, but trying to use your experimental data to validate your CFD won't work, and that is one of the major reasons why some people have trouble validating their CFD. It's not that the CFD is wrong, it's that the air in their density of air in their CFD was different to their experiments. So both the CFD and experiments are right, it's just that you can't compare them because the density of air changed. So get yourself an atmosphere hawk. It makes your experiments much more accurate and your CFD more accurate, and you'll be loving life. You can find it in the link in the description. And I'll see you next podcast. Peace out, amigos.